Okay, so I want to talk a bit about the different ways of looking at constructing quantum classical theories. And the outline of the talk is fairly simple. I'm going to discuss two ways that are figure into this meeting quite directly. The first is the quantum classical Liouville description that we just heard about from Victor Gerasimenko, and also the Koopman approach that is the favorite topic of many speakers and our organizers. And I want to contrast the different forms that these dynamics take and discuss expectation values that are predicted by these theories. Okay, so before getting into the details, I think it's probably not out of place to say a few comments about why one should be even considering such theories. So I think it's well known that there are a lot of attempts in the literature to construct quantum classical theories. Some of them are interesting, others are quite dubious. And it's also known that such mixed quantum classical theories have inconsistencies in them. And in particular, many of these inconsistencies are associated with the lack of a Lie algebraic structure and the breakdown of the Jacobi identity. So in spite of this, it's, I believe, still interesting to think about such theories. And one stimulus, as I've indicated here, is practical. And if you really want to consider very large systems where some degrees of freedom are especially quantum in character, then currently such mixed theories are the only way to approach these problems. And I'm thinking of systems with many thousands of degrees of freedom where certain degrees of freedom are especially quantum mechanical, particularly light mass particles. So this is an example drawn from an old paper that we did years ago, looking at a proton transfer in a complex. So the proton is treated quantum mechanically, and the groups, the phenyl and the amine groups, are treated classically. And this complex is solvated in a collection of solvent molecules, which are, they model a particular species methyl chloride, but you can think of them as real dipoles. I'm doing this for a cluster with just a few solvent particles, but in fact, we've done calculations like this in the bulk phase containing many hundreds. And the intermolecular potentials are quite complex. So in these, I'm going to show you a simulation done using quantum classical Liouville dynamics. You won't see the proton because it's quantum mechanical and treated quantum mechanically, obviously. But in one form where the hydrogen is bound to the oxygen, this complex is essentially has a very small dipole moment, and so the spheres are colored the same. And in the other case, there is a high dipole moment and the spheres are colored different. So you can see a quantum transition every time you see a flip. And this is a picture of the dynamics that results from such a simulation. And this little scale on the left, which you may not be able to read, is the time in picoseconds, and this simulation is running about 150 picoseconds. So what you'll see is occasionally the complex flipping from the same color to two different colors, and that signals a quantum mechanical transition between these two states. And so this is the type of problem that we're interested in studying, and this would be very, very difficult, particularly if you have hundreds of or thousands of solvent molecules to study by full quantum dynamics. So there was a quantum mechanical flip. And there are a number of interesting features about the dynamics that I won't go into here. But in addition to practical issues like this, there of course are interesting questions concerning quantum classical correspondence, measurement, entanglement, and so forth in quantum classical systems. So as I said, I'm going to look at two routes to constructing quantum classical theories. And the first route is what's often considered the usual route. You start with a quantum system and you basically convert that to a quantum classical system by taking the classical limit of one of the subsystems. So I'm going to be dealing with bipartite systems where the quantum mechanical system is partitioned into a subsystem of interest and a quantum mechanical bath. And in this limit, we take a classical limit of the bath. I should make a remark here, and you'll see it later, that when I say classical limit of the bath, because of the coupling, the bath is not really classical, but in the absence of the quantum system, the bath is classical. The other approach is to start with a classical system. Again, now you have a bipartite classical system with a classical subsystem and a classical bath, and you take the limit where you make the subsystem quantum mechanical. So those are the two results. And the interesting feature is that the results aren't the same. And so this leads one to think about this in a bit more detail. So I want to present a quick overview of the quantum classical Liouville equation. And of course, you just heard the talk by Victor Gerasimenko, so I don't need to go into the details. So this equation goes back to his work and the work of Alexandrov. We started somewhat later in 1999 to look at this problem. So you saw the approach. I just want to make one comment. Typically, the way we've been thinking about it in the context of our applications, just like the proton transfer problem, we're dealing with a quantum system where the particles have some characteristic mass little m, and it's coupled to a quantum bath where the characteristic mass of the particles is capital M, with capital M being much larger than little m. So instead of the usual h-bar expansion, you can actually, by scaling that's similar to Brownian motion, cast this into a form involving a small parameter that's the square root of the mass ratio, and the expansion in the small parameter then leads to the usual quantum classical Liouville equation. And the Hamiltonian that appears here is the partially Wigner transformed Hamiltonian that involves the subsystem Hamiltonian, the bath, and the coupling term. So I just wanted to make a few comments about this equation. It has really a lot of very nice features. And as I hinted at earlier, it has one annoying feature, and that's that the quantum classical bracket, which is this combination of the commutator and the antisymmetric sum of the Poisson brackets, it does not satisfy the Jacobi identity. So in terms of the scale variables that I talked about, there are corrections of order mu squared. So this actually produces a number of problems, particularly in connection with the statistical mechanics of such systems. However, there are a lot of good features. In fact, if you look at particularly the chemical physics literature, many of the quantum classical methods that are currently in existence in the literature can actually be viewed as approximations to the quantum classical Liouville equation. So this includes schemes based on linearized path integrals, surface hopping methods, some mean field methods, and the corrections in the scale form at least depend upon the small parameter of the square root of the mass ratios. And there's one other feature that I'm actually going to use in this talk later, and that the equation is actually exact for a quantum subsystem bilinearly coupled to a harmonic bath, or a bath of independent harmonic oscillators. And so that means that it provides actually a very nice way to test algorithms, but it also will allow us to look at some features here without worrying about some of the issues that exist here, because these, since it's equivalent to exact quantum mechanics, then it's simply another way of viewing the dynamics. So the other, excuse me, the other approximation, the other point that I want to make is that the approximation that leads to the quantum classical Liouville equation is really made on the evolution operator. And in principle, you don't need to make that on the initial density. And so In fact, in actual applications of this method, we always attempt to deal with the full quantum equilibrium structure or initial density and only approximate the dynamics through quantum classical Liouville dynamics. And so this actually provides much better results and yields some of the problems associated with the lack of a Lie algebraic structure. But of course, it doesn't solve the issue of the dynamics. But this is an important point that I'll return to later. Okay, so I'm going to be trying to compare with wave function approaches. And so far, we've been talking about approaches based on the density matrix, starting with the von Neumann equation. And so for the rest of the talk, I'm going to focus on systems where the entire quantum initial state is described by a wave function, not a mixed state. One could carry through the argument for the quantum classical Liouville equation with mixed states. That's not a problem, but I want to focus on conditions of this kind. And so the Wigner transform of the initial density then is just the Wigner transform of this initial state based on the quantum wave function. And as I mentioned before, it's such an initial state that I'm going to consider evolving by quantum classical Liouville dynamics. Okay, so one of the questions that you could ask is, can the evolution of such a system, sorry, trying to, the bottom bar is obscuring the screen for me. I don't know if that's in your view as well. So the question is, can we describe such an evolution by a quantum classical wave function? And what's obscured at the bottom is some...
we can see it.
Well, maybe some people are asking questions. Maybe that's why it's here. I guess it's okay.
So we can see your bar. There was just a comment by Jonathan Oppenheim. I don't know if you want to address it now.
Okay. I don't know why that's I don't know why that's not going away. Okay, anyway, it's obscuring a reference to various approaches for constructing quantum classical wave functions. But I just want to say, if as a hypothesis you define a quantum classical wave function as in the line above, then you can show that if this wave function satisfies the equation here that I've shown, then you actually recover the quantum classical Liouville equation. But this equation is quite nasty because it involves the logarithm of the original density. So you actually haven't gained anything by this approach because the equation for the wave function is not closed and requires the density. So you might as well just work with the density. Okay, so now the second approach is the one that I think stimulated this meeting. And I'll just give a brief overview of that. So now the idea is to start with a fully classical system and take the quantum classical limit. So as I said before, now I'm going to talk about a classical subsystem with phase space coordinates little r and p coupled to a classical bath with capital R and P phase space coordinates. By the way, in everything that I'm doing, when I say R and P, these really stand for a vector of quantity. So this is really an n-dimensional system, not a one-dimensional system. But I want to simplify the notation. So the Hamiltonian has the usual form, sum of subsystem, bath, and coupling. And if you have such a system, then the full system satisfies the classical Liouville equation. And some h bars have been added, as is usual in this field, to make it look more like quantum mechanics. But if you cancel them, this is just the classical Liouville equation. So you can define, following Koopman and von Neumann, a classical wave function by taking the square root of the density. And in particular, because the density is the only physical quantity, you can associate also an arbitrary phase with the wave function. And in that case, you can add an arbitrary operator to the that's related to the phase to the evolution equation, and convert that to an operator script L sub h. So if you choose, what I'm going to be doing in the rest of the talk for this is I'm choosing as the phase the classical action. And in that case, the operator L sub h takes the form. So this, again, this bar is obscuring some of the references down here, but this is work by some people at the meeting, as well as our organizers, and the form that the operator L sub h takes is given here. And it basically, it's written in a somewhat more complex form, but it really involves a Poisson bracket over the full phase space plus an additional term that looks like a Lagrangian. So in any event, the procedure for quantizing such a system is to, we want to go to now from a phase space description to a coordinate representation. And so we have to do something with the momentum terms. And roughly speaking, one assumes that the momentum derivatives give 0 when acting on the wave function, and momentum is replaced by the usual correspondence in quantum mechanics. In that case, the operator changes to a quantum classical form, and it involves the Poisson bracket of a quantum classical Hamiltonian and an additional term that is like a Lagrangian, but has extra terms. The quantum classical Hamiltonian has a quantum part, a Bath part, and a coupling. And in fact, this quantum classical Hamiltonian is exactly the same as the one that I wrote down earlier for the partial Wigner representation. And so with this replacement, we have the quantum classical Schrödinger equation that's the topic of this meeting. So here I've written it in basis-free form. That was the R representation. And the expectation value of an operator B is given by something that looks suggestive. L sub B is the same operator that I wrote earlier. Oh, that should have been a K. Sorry about that. With the Hamiltonian replaced by B. And you can also write that as the trace of a density matrix called rho K, but the Koopman, quantum classical Koopman density matrix is a more complex form. And as shown in the papers by Bondor, Ibelmas, and Tronci, the equation for the density is quite complicated, and it is not closed. It depends on the wave function. So it's just the opposite from what you see for the quantum classical Liouville equation. Okay, so now we want to start contrasting these approaches. And so first, let me spend some time just talking about the way one often simulates and thinks about quantum classical dynamics in the context of non-adiabatic dynamics, that is, transitions between adiabatic states. So now I'm going to be dealing with a specific representation of the quantum subsystem, the representation adiabatic states. So the Hamiltonian, we split off the kinetic energy operator of the bath, and the adiabatic states are just the functions of the rest of the Hamiltonian operator that depends parametrically on the coordinates. And I'm calling the adiabatic energies E sub alpha. So you can rewrite the quantum classical Liouville equation in this basis. It contains some pieces which are a classical like evolution operator. You can see it involves the derivatives of the adiabatic energies. These are the Hellman-Feynman forces. If you're dealing with a diagonal element of the density matrix, this is just classical evolution on a single adiabatic surface. And if you're dealing with off-diagonal elements, then you see you have an average of the two adiabatic states and a phase factor that's just the energy gap divided by h bar. The important part that describes all of the coupling in this system between these adiabatic states depends on a non-adiabatic coupling matrix element. That's just the derivative of the adiabatic states matrix element of the derivative operator. And this term is interesting because it's one of the important terms that provides the back coupling of the quantum system to the bath. So the bath is influenced by the quantum dynamics, and you can see that through this momentum derivative. Coupling occurs in other places as well. I want to point out this factor of a half, and that occurs because of the way the dynamics is viewed in this surface hopping picture. So if you want to look at the, if you want to compute the density matrix, let's say of a diagonal element, a population in an adiabatic state at a particular phase point, Rp, then just by iterating this equation, you can see that you have to consider an ensemble of trajectories of this form. You basically evolve on a single adiabatic surface using just this classical evolution operator. And then you have to consider the interactions between adiabatic states governed by this term. So here I'm writing it in an approximation where we exponentiate this term to convert these continuous derivatives into a jump. So this is an approximation. It need not be made, but it's nice to think about this way. So at this point, at some intermediate time, you have a non-adiabatic transition. And then you evolve on an off-diagonal element of the density matrix, and you carry along a phase. So you've created a coherence, and then at some later time, you have a corresponding jump to another adiabatic state, and you destroy a coherence. And really, you have to consider the ensemble of all of these trajectories in order to compute the density at this point. And as an example, on the lower right corner, I show actually all of the trajectories, the initial values of the trajectories, the points R prime, P prime, that contribute to the density at a particular phase point. So you can see it's a very complicated structure of the phase space, and you in principle have to take into account all of these trajectories. To compute average values, it's much easier, and Monte Carlo allows you to sample that. So now let's look by contrast at the Koopman quantum classical Schrodinger equation. So again, I'm now going to project the quantum classical wave function on the adiabatic states, and the corresponding projected Koopman Schrodinger equation again involves a classical Liouville operator. Now it's very simple. It's just the evolution on a single adiabatic surface. It involves a phase factor that's actually just the Lagrangian associated with that state. And it involves a coupling term that looks similar to the one that you saw in the quantum classical Liouville equation. However, there's no factor of a half. And that's because in this jump picture, when you jump between adiabatic surfaces. And so you need the full amount of momentum transfer in order to conserve energy. So you see a difference in the picture. Of course, you shouldn't directly compare these two because you have to actually can then construct the density from this wave function, which is quite complicated to do, but it doesn't change this underlying picture. So this was just to give you a feeling for how differences arise in various simulation algorithms and adiabatic states. But of course, all of these trajectories are basically fictitious objects that are just used to construct average values. And so we don't attach physical significance to them. The physical significance is really associated with observables, and I want to spend the rest of the time talking about these. So if you look at the expectation value of an observable B, then from the quantum classical Liouville equation, it's the usual form. You trace over the quantum degrees of freedom, integrate over the bath degrees of freedom, and you have the product of the operator and the density at time t. And from the Koopman quantum classical Schrodinger equation, it's very similar, except that you now have this Koopman quantum classical density. And of course, it has a more complicated expression in terms of the wave function, whose evolution we know or have an equation for. In order to save time, I'm not going to discuss this full form because it's rather difficult to compare these expressions. But instead, I'm going to consider a simpler case where the observable that I'm looking at is an observable in the subsystem alone. And that means that I can pull it out of the integration over the phase space variables. And as a result, the quantum classical expression is essentially unchanged, but the Liouville expression is unchanged. But for the Koopman theory, you only have to consider the first term in the expression because integration kills these other two terms. But you still have to, of course, evolve those, and the evolution brings in the full complexity. So it's just a simplification in the initial form that you're looking at. And again, I should point out that if you considered Bath observables, you would not have such a simple form. Okay, so now I want to look at a specific simple case, and that's a two-state quantum subsystem coupled to a Bath. So my bases now are 0 and 1, not the adiabatic basis. And in this basis, the Hamiltonian takes a form that I think is familiar to most of you. It looks like a spin boson type form. In fact, this has the structure of a symmetric spin boson system. At the moment, it's a little more general in the sense that I don't necessarily assume bilinear coupling, but other than that, the expression, or bilinear Bath for that matter. And just for notation, for the quantum classical Liouville equation, my rho QC just doesn't have a hat on it, but you should think of it as a matrix in this basis. And similarly, the Koopman quantum classical wave function is expanded in this basis, and I'm denoting the coefficients by C0 and C1 that are functions of the phase space coordinates. And again, I don't know if you can see the bottom of this slide, but the footnote is a reminder that if I consider bilinear coupling and a harmonic Bath, then the quantum classical Liouville equation is equivalent to exact quantum dynamics. And in fact, I'm going to assume that now because that will allow us to really focus on the distinctions between these two and their connection to full quantum dynamics. So at any rate, writing out the two equations for this particular Hamiltonian, you can see they look quite similar. The commutator terms have the same structure. The Liouville operator, classical Liouville operator, comes in the same way. The main difference you see is that this symmetric sum involves the density, the momentum derivative of the density matrix, whereas the corresponding term in the Koopman equation involves these expressions gamma, which involve momentum derivatives of the coefficients in the expansion of the wave function. And so the momentum derivative does not appear on the outside, it appears in this combination. So again, this is general, but now I'll return to the spin boson model itself. So to look at this in a little more detail, I want to consider as an example an entangled initial state. So remember now, I'm referring to what I mentioned earlier, that at least for the quantum classical Liouville equation, which I'm talking about now, I'm going to assume that the initial density is the quantum density, and I'm just going to evolve this using quantum classical dynamics. But again, as I mentioned, for this particular model, it doesn't matter because the partial Wigner representation of this spin boson system is actually exact quantum dynamics, since the expansion in h bar or mu truncates. Okay, so I'm considering an initial state. Remember, I have a bath of independent harmonic oscillators, these refer to the different n oscillators, and their quantum states are n. And so this is a trivial initial state. You could consider more complex ones. So I take all of the independent oscillators in the first excited state or in the ground state, and I construct an entangled state with the quantum subsystem. And the partial Wigner transform of the density matrix associated with this entangled state is given here. The expression you can see involves a density associated with state 1 and the ground state and off diagonal terms, and the expressions for these densities are given at the bottom of the slide. Can you see this, or is it just obscured for me?
Yes, we can see it.
Okay, good. Okay, so the densities are in terms of this f, which is just an exponential of the Hamiltonian, but the denominator is the ground state energy of an oscillator, and similarly the off diagonal elements are complex and are the indicated functions of R and P. Okay, so so now one can try to compare these descriptions. And so for this particular initial density, I've written the initial slope of the that arises in the quantum classical Liouville equation. And so you have the coupling term times a matrix involving the off diagonal elements, and then you have various combinations involving the difference of the populations and the off diagonal elements and classical evolution. But again, in the box, I want to point out a feature that arises in this case, which is that for the quantum classical Liouville equation, you have the momentum derivative of these two population terms that appear here for the Bath variables. Now, it's a little bit it's a little bit tricky to consider how to compare this with what arises from the Koopman equation, because you have to decide really now how to construct the initial state. So it was fairly clear in the quantum classical Liouville equation that you write down the initial quantum system that you're starting with, and then you simply keep the initial state that you dealt with. But here you have to really reconstruct the what you're going to call your classical wave function. And so I've left it fairly general. Just by notation, the coefficient C0 can be associated with some initial Bath wave function, and similarly for C1. And these could be different by simply choosing how you construct the wave functions for those systems. But I think it's something that requires some additional thought, including the phase factors that are associated with these wave functions. But just in from a formal point of view, we can write the equations down for this ansatz. And what you see is that if you look at the first terms in this equation, they're almost completely analogous. Here you have the off-diagonal densities, and here you have the product of the wave functions and its complex conjugate for the two different wave functions, psi1 and 2. So it's reminiscent of an off-diagonal element of a density matrix. Similarly, this frequency-dependent term looks very similar in its structure. The classical evolution term is also very similar in its structure, but this coupling term is different. And it's different because of the way the momentum derivatives appear. The diagonal terms, again, look very analogous, but the off-diagonal terms are different because of the fact that you really started from a wave function description, and the equation is not closed in the density, and you have to retain the wave function. And this has consequences for the observables. So for instance, if you look at the coherence, the off-diagonal, the expectation value of sigma y, the Pauli matrix sigma y, then for the quantum classical Liouville equation, you get this initial behavior. And you'll notice that this term does not contribute because when you integrate over momenta, it vanishes. But from the quantum classical...
8 minutes.
I'm almost finished. From the quantum classical Koopman wave function approach, you have the first term looks again almost completely analogous to the quantum classical Liouville equation, but now you have a second term that comes from the pieces that I mentioned earlier. So even at order t, you have a difference between these two expressions. And again, I keep emphasizing that for this particular model, this is what you will get from exact quantum dynamics. So there is a difference between the approaches in this case, and in the context of the quantum classical Liouville equation, if it were not the spin boson model, you would simply have more elaborate expressions for these gamma functions, but the same conditions would apply. At the bottom, I indicate that if you consider populations instead of these coherences, the differences appear at order t squared, and I didn't write those down. So that was basically the story I wanted to tell. We know that formulating quantum classical theories present a lot of challenges, which is why we're working on it for so long. And not only for fundamental challenges, but also challenges for simulation. But I should mention that it's still, I think, extremely valuable to look at these for both practical and fundamental reasons. And I find it interesting that, and perhaps not surprising, that two different methods for constructing quantum classical descriptions lead to different predictions for the observable. So in particular, I find it interesting to think about how the Koopman approach actually connects to full quantum dynamics in terms of a passage, and how one really gauges the applicability of these approaches. So I think there's a lot of scope for research in this area, and I guess we'll learn about a lot of that at this meeting. Okay, thank you.
Thank you very much for this beautiful talk. So we have time for some questions. Maybe Cesare, you want to ask the first one?
Yeah, well, first of all, thank you very much for this talk, and thanks for sharing these results with us, because I understand these are unpublished results. So let me actually check if I understand correctly. So since you say that in the case you can, so for the spin boson system, for an arbitrary spin boson type Hamiltonian, the quantum classical Liouville equation or the Alexandrov-Gerasimenko equation is basically a copy of the quantum Liouville equation. Do I understand correctly?
That's correct.
No.
Okay. So my first comment is that I mean in a genuine quantum classical theory, I understand that there is a desire for recovering exactly the same full quantum treatment, but a priori, I don't see any specific reason for why a quantum classical hybrid system should be exactly the same as the full quantum system. And second, if I remember correctly, in our paper, we did consider a type of spin boson system in the pure dephasing approximation. And so we did find different results for both quantum classical Liouville equation and the Koopman approach. Was that related to the fact that the coupling in that case was quadratic rather than linear? So these
yes.
are my two questions.
Yeah. So the answer to the second question is yes, I believe that's the case. The first, your first question is an interesting one, and one that we've thought about a lot. And I agree with your general comment. So let me make a few additional comments about that. So if you take a general system, not necessarily bilinear coupling to harmonic path, then then you could ask, what's the structure of the resulting theory, quantum classical theory that arises from the quantum classical Liouville equation? And then all of the issues that you mentioned come into play. So in other words, if you really want to forget about trying to make connection with good approximations to full quantum dynamics, and you want to construct a quantum classical universe based on this equation, then a number of features come into play, then there is no reason to actually try to connect these two directly. And so because of the lack of the Lie algebraic structure, you're not guaranteed that the usual quantum density is in fact a stationary solution of the evolution. In fact, it's not. You can construct equations that give you expressions for the appropriate quantum classical density, but then the entire apparatus of statistical mechanics has to be modified, because you have to construct a set of rules that keeps you within this quantum classical universe. And so it's only for the spin boson model where you it's simply an observation that for systems of that type, if you partially Wigner transform the all the expressions for the expectation values and the statistical mechanical expressions and the evolution equations, that it corresponds to the quantum classical Liouville equation with quantum initial conditions. So that's just a special feature of this particular formulation.
Okay, I'm not sure I understood the specific point about why the two theories should coincide or not. I think what I understand is that you're leaving it open. Am I correct?
Oh, so basically the quantum classical Liouville equation starts from the von Neumann equation and does a partial Wigner transform. And for that particular spin boson Hamiltonian, that general expression that involves an exponential of a Poisson bracket operator truncates to give the quantum classical Liouville equation. But the initial density that you use in order to get exact dynamics is the quantum initial density, which is not truncated. So this is yes. That's the point. Okay. I mean, it's known, from Wigner's work that if you for harmonic oscillators, it's classical evolution with a quantum initial state.
Absolutely. Thank you.
Maybe let's take quickly two more questions. I think Jonathan Hoppenheim had a question.
Let me say a few words. Okay, it's a big pleasure, Raymond, to see you. Thank you for the wonderful lecture. I am really obtained great pleasure, and I am very glad. Thank you. I hope we will have opportunity during the conference speak some more about quantum classical system. Okay.
Yes, definitely.
Thank you. Thank you. Thank you.
Yes.
My greetings.
Yes, sir, I just had a question. So in the beginning, you mentioned that something that annoyed you was the failure of the Jacobi identity to hold. And I was just in both directions wondering why you weren't more bothered by the failure of complete positivity to hold, which seems
Okay.
to me
So
more of an issue. And I guess I was interested in what is it about the failure of the Jacobi identity to hold that bothers you? And
yeah.
And we find in the case of general relativity that actually it does hold if you have some constraints are satisfied. So I'm wondering, my motivation for the question is just wondering, what I might lose otherwise.
Okay.
Presumably some gauge invariance.
So with regard to the positivity, that of course is a feature of the partially Wigner or Wigner transform density. But the way we actually view it is that we primarily focus on the computation of observables. And so when we actually construct an algorithm to find the expectation value of an observable, we don't sample from the density. We actually sample from a positive definite form, and we reweight the observable to account for any of those deviations from positivity. So if you can compute the expectation value using the Wigner density, even if it's not positive, because it's just an identity. And so that's the way we handle that issue. So with regard to the Jacobi identity, it bothers us primarily in the statistical mechanics, because when you want to construct a transport property like a rate coefficient or some other transport property, then the quantum mechanical expression for that transport property is given in terms of a Kubo transform correlation function. And if you try to work through the corresponding expressions using the quantum classical bracket, then you find that those expressions break down. And a lot of the manipulations that you make, so for instance, if you have a correlation function involving operator B at time t and A at time 0 averaged over an initial equilibrium density, then all of the usual manipulations that you make in either quantum or classical mechanics, say for instance, the evolution of a product of operators is the product of their evolutions, does not hold. And so that's because of the breakdown of the Jacobi identity. So it produces a lot of annoying things that you have to deal with if you don't do it. And so the fix that I showed at the beginning, where you keep the quantum structure and the partial Wigner transform of those quantum expressions, gets you out of that a little bit, but these are issues that come up in the statistical mechanics.